Okay, I want to welcome all of you from all around the globe to our PolarConnect event. We are really excited to be talking via satellite phone with Jamie Esler and the rest of the research team. They're in Iceland. I am not going to pronounce the name of that glacier. We'll let me and others do that here in a little bit. But they're looking at Drumlin Formation, and today on Wednesday, 2013, we're going to learn all about glaciers and drumlins. I'm very excited to hear more about that. I hear lots of people joining us. Welcome to this event. We do have Jamie online. He's via satellite phone. He may come and go throughout the presentation today because of the satellite technology. We will not be doing video, and we will not be able to see text or comments from Jamie and the team. I will have to relay questions and things to that. So while I'm pushing up the next slide, I heard a few beeps, and I want to make sure that Jamie is still there. Are you there, Jamie?
Yes, I'm still here.
Okay, great. Hard to tell with all the beeps of other people joining us what's going on. So the next slide, just to get people in the virtual world oriented, is a slide showing Blackboard Collaborate and some of the features that we're using. If you want to talk later on and ask your questions in person to Jamie and you're using voice over IP and not the phone, you will need to click on the talk button once, hold down the talk button to open up the mic, talk away, ask your question, and then click on the mic when you're done talking. If you have a question as we go along, you can click on the little hand icon above the list of participants. And you can ask your questions in the bottom in the chat window, and I will relay them to Jamie and team. If you're here joining us by a telephone today, it's important to keep down the background noise, so press *6 on your phone to mute it and *6 to unmute it. And today's event will be archived and we'll post it online when we're all done. A few little more things. We don't have time to go around the room. I will send Jamie and the team the list of participants for today, but just so you know, Jamie, we have an outdoor leadership school, Selkirk that joined us, Lynn Esler joined us,
Right.
Jan Parks joined us, Nancy Gooden joined us. I think that's all the new people. So lots of people joining us. Tell us where you're from in the chat window and give us an idea of who's with you. A little bit more background about why the heck Jamie is all the way in Iceland looking at glaciers. He's part of a program, if you haven't figured out by now, it's called PolarTrec. And we place teachers like Jamie from around the United States with researchers in the polar regions, both the Arctic and the Antarctic. It's a National Science Foundation funded program operated and administered by this nonprofit, a little old nonprofit called Arctic Research Consortium of the United States. We're based in Fairbanks, Alaska. That's where I'm talking from today. And we try to get teachers out working with researchers so they can take these experiences back to the classroom. And Jamie is one of the lucky teachers in the United States that gets to work with a great science team. So we're really excited to hear more about what he's been doing. Just one more thing before we go into the presentation with Jamie. If you have a question, like I said, type it in the text box, and I'll try to interrupt and relay it to Jamie at a good time. And at the end of the presentation, you can click on the little hand icon, and we'll call on you. And if you're by phone, I'll try to remember that you're on phone and not on the Internet, and we'll also let you ask your questions. So with that, I'm going to turn it over to Jamie and let you talk. So Jamie, we're on your first slide, and just cue me when you're ready for the next one.
All right. Well, hi, everybody. Thank you so much for taking your time to connect with us today. Right now, it's about 10 o'clock at night. In the cook tent with Reba and Libby, Dr. Iverson, Jeff, and James. And it's pretty cool and wet out. We got our first little bit of rain today. We're all alive and well and happy and healthy, and things are going great. And we're very well fed. I'll get into that later. So this project is titled Testing Drumlin Formation Hypotheses in Central Highlands of Iceland. And the hypotheses is plural, as there are two primary hypotheses which explain the formation of this glacial landform called the Drumlin. And the Drumlin is a long line, elongated hill of till, which is a certain type of sediment that's created by glaciers. And till can be created in many different ways by glacial systems. This particular till is formed subglacially at the bottom of glaciers, and therefore drumlins are formed subglacially at the bottom of glaciers. And so this study is looking at these drumlins, and what's especially important about that is that this is the only known active drumlin field on the entire planet. There are drumlins found all over the place, from Antarctica to upstate New York and throughout the Midwest. Many of those are tens of thousands or hundreds of thousands of years old from the Pleistocene epoch, a previous geologic time period. Whereas these drumlins here at Muleyjokul are fresh. We're looking at a live geological event happening, which is significant for the glaciological and greater scientific community. Can you still hear me?
Yep.
Okay, great. Next slide, please.
You want to come and look, Mom?
So who we are, here's the team. I'm going to start in the top left. There's Dr. Neil Iverson and Dr. Tom Hoyer from Iowa State University and University of Wisconsin-Milwaukee. They are the PIs on this research grant, and they began their study on the Muleyjokul forefield and drumlin formation last year in 2012. Clockwise from there is PhD student Reba McCracken from Iowa State University. Below Reba is Jamie Esler, that's me, myself, from Lake City High School in Coeur d'Alene. Below me is James Amato, an undergraduate student from University of Wisconsin-Milwaukee. To the left of James is Libby Woodford, a master's student at University of Wisconsin-Milwaukee. Next from Libby is master's student Jeff Gadd of Iowa State University. And above Jeff is Dr. Luke Zoot, a postdoctorate researcher at Iowa State University. And in the heart of our team is science educator and chemistry instructor from Drake University in Des Moines, Iowa, and our new camp mother, Sandy Tomer. And I picked that photo because she's serving up a very delicious pear cobbler that made us all very happy a few nights ago. Next slide, please. Can you still hear me? Are we still connected?
Yeah, we're still connected.
Great. Okay, so where we are, this image is from Google Earth, and you can see the glacier Muleyjokul coming through a confined valley of mountains, and Muleyjokul runs off of a larger continental ice sheet called Hufsjökull. The red arrow on top indicates the location of our base camp where I am now, and the arrow below that is the general location of our first drumlin sampling site that we've been at the last 5 or 6 days. Muleyjokul is a surge glacier, which means that it periodically advances and then retreats back where it came on a fairly regular cycle. And the last surge that it experienced was in 1992. Next slide, please. This is a picture from the helicopter that I took on our way in. I really like this one because it gives you a neat perspective on the terrain that we're in. Am I still connected? Hello?
Yep, you are.
Okay. Okay. So you can see the two tents in the foreground there. That's our base camp, and the yellow line running up through the center of the screen is the approximate hike that we take each morning to get to our sampling site. It takes about an hour, maybe just over an hour, depending upon the weather, to get to our sampling site. And we're hiking through very, very rugged, rocky, wet, mucky, muddy terrain to get to the sampling site, which at the very end involves perhaps a 300-meter, no, maybe 200-meter traverse over the ice to get to our sampling site. Next slide, please.
Okay.
So how we got to our location was by helicopter through Hilo, Iceland, and that took a good portion of August 1st. We had a total of, I believe, 5 or 6 sling loads of people and equipment. It was an absolutely beautiful day to get in. No wind, sunny skies. It was a glorious day to be transporting in to our base camp location. Next slide, please. In this photo, you can see on the left, for scale, the size of these bags that we used to get our equipment in. They were kind of like heavy-duty, reusable grocery bags that were very large, that would attach to a long cable with a metal hook to the bottom of the helicopter. And we took 2 at a time. And on the right, you can see Dr. Tom Hoyer and Libby Woodford enjoying the helicopter ride into base camp. Next slide, please.
Okay.
All right, let's get down to it. Why we're here. Dr. Iverson and Dr. Hoyer are testing 2 competing hypotheses for how drumlins are created by glaciers. The first hypothesis is from the late 80s, and it's referred to as the Bolton hypothesis, which basically states that drumlins are depositional landforms. More details on this in a few moments, but essentially this would indicate that the glacier is depositing or releasing till into the shape of the drumlin. The alternate hypothesis states quite the opposite, that drumlins are a result of erosional forces which would remove till from around them, leaving their shape intact. And in that photo you can see for scale there's some team members standing out on the drumlin. This is the second drumlin that we're going to be testing actually tomorrow, I believe. We're going to make our way out onto that drumlin. Next slide, please, Janet. Okay. In this photograph, this is another photograph from the helicopter ride. These 2 large red arrows are pointing at 2 drumlins coming out from underneath Mulioko's ice margin. This is a very significant photograph because it shows how this is an active environment to the formation of these landforms. Portions of these drumlins are still hidden beneath Mulioko's ice, with portions of them being exposed. Next slide, please. At this point, I'm going to turn the phone over to Dr. Neil Iverson, one of the PIs on the research proposal, and he's going to continue to go over the why exactly we are here in the Highlands of Central Iceland.
Hi, everybody. I just want to talk a little bit more about drumlin formation in this slide. Can you guys hear me?
Yep, we hear you great.
Okay. I just want to talk a little bit more about drumlin formation. Drumlins are these elongate hills that form beneath some glaciers, and you can see one in this slide, one that we're working on. Lots of glaciers, including this one, rest on sediments, not on rock. And so the question is, why are these sediments organized into hills? And what we're trying to figure out is whether the sediment accumulates preferentially to make these hills, or whether erosion occurs around the periphery of these hills or around the periphery of sort of a rigid core, and that rigid core becomes eventually a drumlin. So we have a variety of measurements laid out that Jamie will talk about in just a minute. I think you can go to the next slide.
Okay.
So really we have measurements aimed at studying two things. One are patterns of deformation in the sediment beneath the ice. Does the movement of the sediment beneath the ice form these hills, or is that sediment movement not very important? Those are the sorts of questions we're trying to answer. The other thing is we have measurements aimed at trying to understand the stresses that cause sediment to move beneath the glacier. If we can understand those stresses, then we can say something about how sediment is moving around. And so what makes this place particularly good for studying this is that we have lots of imagery of the glacier surface when these drumlins were being formed. So we have a lot more information about the glacier dynamics than we would looking at hills, say, from the upper Midwest that are 15,000 years old. So at this point, if you go to the next slide, Jamie will talk about some of the kinds of measurements we're making.
Okay, and before Jamie talks, I know there are some people that just joined by phone and are following by PDF. And I just wanted to let you know the slide that we are now on is what are we doing? It should be about slide number 16. What are we doing and about data collection. Okay, Jamie?
Okay, so this graphic organizer shows the three primary types of data that are being collected for this project. On the left, you'll see AMS, Anisotropy of magnetic susceptibility. In the middle, you'll see pre-consolidation testing and bulk density. And on the right, GPR, ground penetrating radar. So I'm going to go through each of these three data collection methods in the following slides. So Janet, next slide, please.
Okay.
Really, before any data can be collected, there's a lot of digging that has to be done because we have to access fresh layers in the till, so to say. These drumlins get covered by another type of sediment called colluvium, and to access the till we have to dig in and find the till particles in situ or where they've been previously before we dig into them. So we do this manually quite a bit, and we have the help of some two-stroke jackhammers. Next slide, please. And the jackhammers make this job much more efficient by breaking the clasts in the till up, which can then be shoveled out to expose our excavation pits. Next slide, please. This is another significant picture because it shows our first testing site. This is in a stream cut through a drumlin, and this is significant because it allowed the team to sample for pre-consolidation, bulk density, and AMS sampling at greater depths in the drumlin. The stream in itself kind of did the excavating for us, and we're now able to sample much lower in the drumlin than we otherwise would have been able to. Next slide, please. In this picture, you can see Reba and Tom and Neil excavating a bench-type pit at the very top. And just off to the right and below them, you can see a secondary excavation pit at a different depth in the drumlin. And this is significant because we need to get a good amount of spatial data through the drumlin to have consistency and meaning in the data that are collected. Next slide, please. So AMS, Anisotropy of magnetic susceptibility, these are the data that and measurements that Dr. Iverson mentioned that are helping to trace this fabric of how the till has been moved into place. And it requires a lot of tedious work on our hands and knees with very small plastic cubes that are approximately 2 centimeters, is it 2 or 3 centimeters? 2 centimeters in each dimension across that are pushed down into the till and then ideally removed. Next slide, please. In this picture, you can see how these cubes are pushed into the till using a steel tool that allows pressure to be exerted on the top. And ideally, we get this fabric of samples all pointing in the same direction or aligned in the same direction. Next slide, please. So the process involves getting them in the till first, marking them with a Sharpie, excavating or extracting them. The tops of them are cleaned with this thin wire saw. Then they're capped and they're stored in a bag. This has been much easier for Dr. Iverson and Dr. Hoyer and their students back home with tills in the Midwest of the United States. This particular till here in Muleyoko is very rich in pebble and cobble-sized clasts. And so if you go to the next slide, please, you can see that a great majority of our samples come out looking something like this. And the success ratio of samples actually taken and kept is quite low compared to how many samples are attempted. Next slide, please. The pre-consolidation testing is a common test used by engineers, and this is being applied in the till here to try to identify how there might be pressure gradients within the till, to determine if it's able or was able at one point to move from areas of high pressure to low pressure. Similar to how toothpaste or any other fluid-like material can move from an area of high pressure to an area of low pressure when it's pushed or forced. Next slide, please. Here are some photos for how these are completed. In the top left, you'll see that there's a mallet which strikes the top of a driving type tool, which sinks this brass ring, a beveled edge on the bottom, and drives it into the till. Once the brass ring is successfully inserted into the till, it can be excavated out and cleaned with this wire saw again, and put between two metal plates, which is then taped quite tightly together and also wrapped in plastic wrap and then stored in another bag from there. These are even less successful in this till than the AMS samples. James, what do you think your success rate is on these? Maybe James has been doing a lot of these tests, and we're estimating a success rate of about 10%. So maybe 1 in 10 of these goes well. Same idea. The ring just gets dinged up by the large class in the till, and you have to start over. Next slide, please. Are we still connected?
Yes, and just real quickly, a couple things. For those of you that are following through the phone, we're on slide 27, ground penetrating radar. And then Jamie, I have several questions in the queue for you. So whenever you feel there's a good stopping point.
Okay, great. Okay, so the ground penetrating radar utilizes electromagnetic waves. These are the same type of waves that come out of your cell phone or come out of an X-ray tool at the hospital, or visible light is an electromagnetic wave. These are radar waves, and so they're much lower in frequency, waves per second, and they're much greater in their wavelength, the size of the wave. But as far as their composition, it's a magnetic wave combined with an electrical wave, transverse waves together. And this device shoots these waves down into the till to help identify macroscopic structures in the subsurface till of the drumlin. So we can actually get really nice imagery of what's down beneath our feet on top of the drumlin. I've been helping Dr. Zolt with this quite a bit. In this image you can see us getting ready to pull the GPR in, oh, I don't know, 50-mile-an-hour winds that day, I think, maybe 40 mile an hour. Next slide, please. What the tool actually does is it measures a difference in electrical transmissivity, which is a measurement of how easily electricity moves through the particles in the sediment. In the image in the lower right-hand corner, you can see definitive layers in the till below us. The y-axis represents depth, and we would be standing at the very top of that graph of data. Shannon, I believe this would be a good time for any of those internet questions before we go to the next slide.
Okay, great. Yeah, there's 3 questions that have come up online, and maybe there's some by phone as well. But the first one is from Carol, and she wants to know, why have we not been able to see active drumlin formations in other retreating glaciers?
That's a really great question, and drumlins do not form near all types of glaciers. So they're a very specific landform to particular types of glaciers. So valley glaciers, for instance, or glaciers that are confined to tight mountainous valleys, common throughout, well, used to be more common throughout the Rocky Mountain West, and common throughout northern British Columbia and Alaska and other regions. Their physical properties do not generate these type of landforms. They're much more characteristic of larger continental ice sheets as opposed to valley glaciers.
Okay, and then let's see, what's the next one? Austin, who's at the library, would like to know how many active drumlins are there at the moment?
It's a great question. Right now here at Muleyokul, there are approximately 50 of them that have been formed recently or are currently in the process of formation.
Okay, and then Kitty would like to know, are surge glaciers the only type of glaciers that form drumlins?
Are surge glaciers the only type of glaciers that form drumlins? No, they're not. I'm going to pass this off to you. I'm going to pass off to Dr. Iverson for this one.
Okay.
So I guess the question is whether surge type glaciers are the only kind of glacier that forms drumlin. And there are drumlin fields all over North America and Scandinavia and the UK from the last glaciation. And many of those drumlin fields were likely not formed by surge type glaciers. This glacier we are working on is a surge type glacier, and so it may well be that the fact that this glacier surges is not necessarily relevant to the formation of these hills. It may be something that is is shared by glaciers that aren't surge type that gives rise to drumlin. So, but that's a good question. I'll hand you back to Jamie.
Okay, thank you.
Janet, is it okay if we go to the remaining 2 slides?
Sure. Yep. And I've got 3 more questions lined up. So we're on.
All right.
For those following by phone, we should be on why this is valuable research, slide 29.
Yeah.
Okay.
So why this is valuable research, there are many different answers to this, and we've been speaking a lot about it, not only here in the field, but on the phone over the last few months and in email exchanges in preparation for our time together out here. In a very broad sense, this is important because understanding glacial behavior impacts computer models, very, very advanced computer models called GCMs, which are used to help geoscientists predict future climate change. And in the age of increased atmospheric temperatures across the world, measurable increases, we're noticing a strong correlation and decline in glacial mass balance. And so we're seeing that as global temperatures rise, glaciers are melting, and one of the most direct effects of this glacial melt is rising sea level. With hundreds of millions of people around the world living in coastal regions, this is a very significant thing for the scientific community to try to understand as thoroughly as we possibly can. And so drumlins themselves may very well affect the subglacial movement of glaciers. So not only does the glacier create the drumlin, but the drumlin may affect how the glacier behaves. And so the more we know about how glaciers move, the more accurate our predictions about the future of climate change may be. Next slide, please.